Exploration-exploitation trade-off is a fundamental concept in reinforcement learning that describes the balance between two competing objectives, exploration and exploitation. The agent tries new action to discover potentially better reward or strategies. So that is exploration. And exploitation, agent uses the knowledge it already has to maximize rewards by choosing the best known action. So before we look into the example, let's understand why trade-off is important. So exploration is necessary to ensure agent doesn't miss out the better option or strategies that hasn't tried yet. Exploitation ensures the agent leverages its current knowledge to achieve high rewards efficiently. So let's understand this from the snake game perspective. Imagine an agent is playing the snake game. So exploration, the agent might move in random directions. So this is important, random directions, even if it means dying to learn how environment reacts and which moves are safe. Okay. So for example, there is a wall and the snake is here and the snake randomly chooses the direction and hits the wall, right? So with this step, snake will learn that hitting the wall is a bad move. The snake will receive the negative reward. Exploitation, the agent deliberately takes a move it knows increases its score, such as moving towards food based on the past experience. So in exploration, agent randomly chooses the direction and store that knowledge, the outcome, right? Then in exploitation, agent uses this knowledge to determine the best move. That is, should not hit the wall or move towards the food. So trade-off, why trade-off is important. Okay, these are the same points. Let's move to the next slide. Let's clear the screen. Now let's discuss about methods to handle the trade-off. Okay. First, Epsilon-Greedy policy. A common approach where agent chooses a random action with probability epsilon and the best known action with the probability 1 minus epsilon. And over time, epsilon is gradually decreased to favor the exploitation. The second is decaying epsilon. The value of epsilon starts with high, let's say 1, for more exploration. It decays gradually to lower value, 0.01, favoring exploitation as the agent gains more experience. Okay, so initially epsilon value is 1. Let's say this is the snake game and this is the snake. So initially when the epsilon value is 1, all the moves of the snake would be random. Okay, so basically a snake will randomly explore the game and store all the knowledge or outcomes from those random moves. And over the period of time, the epsilon value will gradually decrease. What that means is a snake will exploit the knowledge which he has gained through the random moves during the exploration. So again, when game begins, a snake will take all the random moves, gain some experience, and then use those experience to make better decisions. Okay, let's clear the screen. So our epsilon starting value would be 1 and the epsilon ending value 0.001. Okay, so this one. So here it is 0.01, but we'll go with 0.001. Now next is epsilon decay value. So we are going with 0.9995, rate at which epsilon decreases over time. So we'll start with 1, we'll end with 0.001, and we'll decrease with the rate 0.9995. As you can see, it will take long time to decrease the value of epsilon from 1 to 0.001. Okay, so we want the snake to explore for a much longer time before the snake starts making the decisions. Next, we'll create a function, get action. So get state function determines which action agent should take in a given state. Also, it balances exploration and exploitation. So remember, we had discussed the exploration and exploitation trade-off. This function will handle that. So first, this function will use the local queue network to estimate the action value for a given state. So this function needs the state for which it needs to get an action. So the get state function returns the numpy array. So first, we need to convert this numpy array into PyTorch tensor. So let's do that. So state is equal to torch dot from numpy state, then convert to float, unsqueeze, and then to self dot device, and here 0. So first we'll convert the numpy array into PyTorch tensor, then we'll convert it to float needed for the neural network, and unsqueeze 0. So this adds a batch dimension because Q network expects input as a batch of states. Move the tensors to the correct device, GPU or CPU. So now we have the state. So now self dot local network dot eval. So what it does, it puts the Q network into evaluation mode. That means disables features like dropout and batch normalization that are only used during training. And at this step, we are not training, we are evaluating. Now with the torch dot lograd action values self dot local network, and we'll pass the state. So this torch dot no grad is to ensure that no gradients are calculated. So this saves memory and computation while we compute the action values on the local network. So now we have Q values for all the possible actions. So it would be something like list of Q values for each action. So state and action underscore 0, action 1, and so on. So in our case, the action size is 4. So we'll get 4 Q values. Now, before we do anything else, let's put back the Q network to the training mode. So self dot local Q network train. Next, we will select the action with the highest Q value. So we'll have the move torch dot max action values dot item. And with that, we are done with the exploitation part. That means agent uses the knowledge it already has to maximize rewards by choosing the best known action. So we are choosing the best known action. Now the exploration part, where agent might move in random directions to learn how environment reacts and which moves are safe. So we'll add some random moves here. So random dot int 0 to 3. So why 0 to 3? Because our action size is 4. So this will give values either 0, 1, 2, or 3. So now we have the random move, and we also have a move computed from local network. And we'll choose one of this move based on the Epsilon-Greedy policy, which trades off between exploration and exploitation. So what we will do, if random dot random is greater than epsilon. So this function will also take epsilon as a parameter. So if greater than epsilon, then choose the move from local network, else pick the random move. And here return move.